Hello everyone, welcome back to Manarat Academy and yet to another video. This time we will be explaining this physics paper 4 paper. This is October-November 2025. It was last year's paper. And this paper here consists of about 20 pages with any blank pages. So let's get started. Alright, so let's start off with question number 1, general physics. State the difference between a scalar quantity and a vector quantity. Now you can explain this question from either perspective. Either you can explain from the perspective of a scalar quantity or that of a vector quantity. In my case, I would explain from the perspective of a vector quantity. I will say that a vector quantity contains both a magnitude and a direction. If I want to, I can also talk about the scalar quantity, in which the scalar quantity only contains a magnitude. This will be my answer. So, vector quantity contains both a direction and a magnitude. And what do I mean by a magnitude? Now, magnitude is just essentially the number, the raw numerical data. That is magnitude. So, vector has both a direction and a magnitude, while scalar only contains the magnitude. Okay, I hope this is clear. If it is clear, then we can just move on to the next part. Part 2. In the list below, draw a line under each of the quantities that is scalar. Okay. So first of all, acceleration is not scalar, it is vector. Because it comes from velocity, change of velocity over change of time. And since velocity is scalar by itself, or I mean vector by itself, this would mean that the whole quantity here will be vector. So it cannot be acceleration. Mass, on the other hand, is scalar. Now, let's say here that one of the options here was weight. Now, weight, this one here will be the vector quantity, while mass is a scalar quantity. Weight essentially is the force that pulls a person or basically pulls an object towards the center of the air. Mass is just its mass, the amount of quantity of an object. So this one is scalar. Momentum comes from mass times volume, or I mean mass times velocity. And once again, velocity is vector, which means that the whole quantity by itself is vector, so it cannot be momentum. Okay, electric field strength. Electric field strength. Now this one, it might be a bit tricky, but you need to understand that electric field strength is what can pull an electron or a proton into a plate, either if it's positive or negative. Since it's pulling an electron or a proton in a certain direction, then this means it's vector, just because I mentioned that there's a direction. It is pulling to a direction. It's not only a numerical value, it is also a direction related to that numerical value. And actually, we'll see this one here later on in this paper. So, it is not this one here. Energy. Energy is scalar, is not associated with any direction at all. So as temperature. Temperature is also scalar. So our final answers here will be mass, energy, and temperature. To get all of the 2 marks, the full credit, you need to have all of them. Mass, energy, and temperature. Okay, moving on. A 3 marker over here. A tennis player throws a tennis ball into the air. The mass of the tennis ball is 5.8 times 10 to the power of negative 2 kilograms. The tennis ball leaves the tennis player's hand and reaches a maximum height of 5 meters above the point of release. For part I, show that the initial velocity of the tennis ball is 9.9 meter per second upwards. Okay, now you might be asking, how do I tackle this question? So what you need to do basically is to first of all highlight the main quantities. Here you have the mass m being 5.8 times 10 to the power of negative 2. Okay, and then the maximum height is 5 meters above the point of release. Okay, so to visualize it here, we have the ball over here from the hand. Consider that this is a hand, a very bad drawing of a hand, but just consider it as a hand. This hand will basically launch this ball upwards until at some point the ball will lose momentum and then it will drop down back. So basically, it will gain kinetic energy. Here, it will lose all of its kinetic energy in favor of potential energy. And then the potential energy decreases as the height decreases, causing an increase in kinetic energy again. So what am I trying to say here? I'm trying to say that here we can apply the principle of conservation of energy. Kinetic energy is converted to potential energy and vice versa. So this is basically what we want to use. Kinetic energy will be equal to, in this case, to gravitational potential energy. Okay, so what do we do here now? Kinetic energy, as we know it, it is half mv squared, while GPE, which is gravitational potential energy, will be mgh. Now we can already see that we don't really need the mass. We can just cancel out the mass. So we don't really need the mass m here for this calculation. We might need it in the later part, but as we are concerned, as far as we're concerned here, we do not need the mass. So we can just do a quick rearrangement. So v squared will equal to gh, or more frankly, 2gh, and v by itself will be the square of that. So it will be the square of 2gh. Okay, so far so good. So since we have our formula, since we derived our formula, what we can simply do is that we can just put on all of the values. Okay, now g here, in previous specifications of the syllabus, it used to be 10. But from 2023 onwards, and if you look at the cover page here, you can see that take the weight of 1 kilogram to be 9.8, aka acceleration of free fall being 9.8 meter per second squared. And this is what we'll be using here. So square root of 2 times 9.8 times the height being 5. Now you can just use our loyal friend, our calculator. So 2 times 9.8 times 5, what will that give us? That will give us 7/2, which will be about 9.899. However, if you look at the question here, you can see that all of the values are to two significant figures, meaning our answer has to be to two significant figures, so it is 9.9. And this matches exactly with the answer here. Thus, we have actually shown the condition. So it is 9.9, and we should get full credit here as long as you don't skip any points or any steps. Okay, moving on. Calculate the momentum of the tennis ball as it leaves the tennis player's hand. Okay, here we will actually use the mass that we initially discarded. So the momentum here will equal to mv, mass times velocity. So it will be the mass being 5.8 times 10 to the power of negative 2. And since it only asks about the tennis ball when it leaves the player hand, then we don't really need to consider this part here in which the ball returns to the player's hand. So this would mean that we only need to multiply by the velocity by itself. We don't need to do 2 times velocity. So that will just essentially be the velocity that we calculated being 9.9. However, I do not recommend here using 9.9 by itself. I recommend that we use the original value being 9.899. Now in this case, it won't make much of a difference since it is 9.9 anyways, but some other questions or like some other scenarios using the original value will actually have a significant difference. So be very careful with this point here. So 5.8 times 10 to the power of negative 2 times 9.899. What do we get? We get 0.574 rounded to two significant figures. That would be 0.57 kilogram, don't forget the unit, kilogram meter squared. Or meter per second, my bad. Meter per second. So 0.57. Now, alternatively also, instead of writing that, you can write it this way. 0.57 kilograms meter second to the power of negative 1, or to the 1. Now, this is more scientifically accurate, but as far as we're concerned for IGCSE syllabus, you are totally fine and you're perfectly fine with using this notation here. Okay, so we're done with question number 1. Hope that's clear. So let's move on to part 2, question number 2, part A. A truck moves with a constant acceleration. The speed of the truck increases from 13 meters per second to 22 meters per second. The time taken for this increase in speed is 4.5 seconds. The mass of the truck is 3,700 kilograms. Calculate the resultant force acting on the truck. Okay. Now what we can see here is that we have the speed as well as the time. So here for the resultant force, we can take advantage of the formula being force equals to ma. Force equals to mass times acceleration, with the mass being 3,700 kilograms. But for this, in order to use it, we need to find A, acceleration. So acceleration will equal to delta V over delta T, aka the change in velocity over the change of time. So what you'll be doing here is that we'll be subtracting 22 from 13, and then we divide that by 4.5. Now, of course, so we just do basic mathematics. That will be 9 over 4.5. And this will perfectly be 2. So acceleration is 2. So if you want to get our mass, or resultant force, that will be mass times acceleration, being 3,700 times 2. And that would equate to 7,400 newtons. Do not forget the units, since it is not provided in the question. Had you not written the units, you will not get full credit for your answer. So be very, very careful here. Alright, so part 2. The engine of the truck provides the forward force on the truck. State two forces acting on the truck in the opposite direction to the resultant force. Okay. So essentially what we have here is that we have a road, we have a truck here. Consider this a truck. Looks more like a bus, but the idea stands. We have a truck over here. This truck will be exposed to both the air in the environment or in the atmosphere, and also it will be running on the road, which means that it will have air resistance or drag from the air as well as friction with the surface of the road. So these will be the two forces. And since here it only says to state rather than describe or explain, we are perfectly fine with just stating the names, being friction with the road, that's one, and the second being drag or air resistance over here. Now, since I already said air resistance, I don't need to say air resistance with the air. Though you might need to if you've written drag. Air resistance by itself is perfectly fine. Okay, an interesting looking question. Let's see what this is. Part B, figure 2.1 shows a car as it travels round a circular track. A racing track, okay. Now this is a circular track over here, okay. Part 1 says the car travels at constant speed. Figure 2.1 In figure 2.1, draw an arrow to show the direction of the force acting on the car. Okay. First of all, we have the velocity. Of course, that will act like so. This is the velocity. And we also have the force that points towards the center, as being the centripetal force. And this will also act as our resultant force. And since here it says an arrow implying only one force, we don't really need to show velocity, since after all it's a unit of direction and magnitude rather than actually being a force. What really is a force, however, is the resultant force being the centripetal force, which points towards what? Towards the center of the track, because after all it is circular. So this will be our centripetal force. Okay, so that's already one mark done. For part 2 here, a different car travels around the same track and slides off the track at point P. Okay, so at point P, the car no longer is on track, so it just had slidden off the track. So probably it will be crashed by the barrier by then. Okay, so now state two possible reasons that causes the car to slide off the track. Okay, two possible reasons. One reason that you can think of is, after all, what's really keeping the car on track is friction. Okay, it's friction that is keeping the car on track. Now think about let's say the an ice skating rink. When you're ice skating, if you have experience with ice skating, you would know that actually, well, gliding on ice has minimal friction compared to just walking on a regular surface. This is because there isn't much grip on the surface. The same idea applies to the car and the track. The car has friction on the track, which is keeping the car on the track. If, for whatever reason, that car had lost traction, then essentially what will happen is that this car will slide off the track because it doesn't have enough grip on the track. So a lot of friction will cause the car to essentially glide off or slide off the track. So that's our first possible scenario or reason. Loss of friction with the surface. Okay, okay, that's nice. That's already 1 out of 2. Our second scenario, or second possible scenario, is that the car could be going too fast. Because the car is going too fast, then actually the value of the velocity will be greater than that of the centripetal force. So the resultant force will be transferred to the direction of the velocity, which will cause it to immediately slide off the track. Okay, so let's try to visualize it. So our first scenario, in which there was a loss of friction with the surface, what's going to happen actually is that the car would slide towards the center, because that is where centripetal force is. So it will slide towards the center. Meanwhile, if the velocity was too high in our second scenario, then that will basically outweigh the centripetal force, which will cause this car to slide towards this barrier here. So these are two scenarios that have two different outcomes. However, as you can guess, both of them will end up crashing. So not a good outcome for either. So for part 2, essentially here, our second answer will be increased speed, or we can say excessive velocity. Excessive velocity. Now here you don't need to explain because it just said state. So you don't really need to explain what will happen subsequent to this event. Alright, let's see what we have here for question number 3. Figure 3.1 shows black solar panels installed on the roof of a house and a large rechargeable battery. Okay, a very standard setup. The solar panels produce electricity and give a maximum power output of 3.5 kilowatts, which is basically 3,500 watts. The efficiency of the solar panels is 16%. State and explain, huh? Okay, this time you have to explain, not only state. State and explain one advantage of using black solar panels. Okay, the advantage of using black solar panels is more electricity will be generated. So, this is that. More electricity will be generated. That's for one. However, we still need to explain. And the explanation is because black colors or darker colors are better absorbers. Okay? So, black colors are better absorbers. So let's say here, what we can say essentially is black solar panels are better, or you can say more efficient absorbers. Okay, so that is our answer over here. Okay, for part B, this is where we come back to calculations. So calculate the power received by the solar panels from the sun. Okay. Alright, so efficiency would look something like this. That is the formula for efficiency. Essentially, that will be output power, or like useful power, over input power, or basically total power, times 100. In this case, here, that was 16%, and this is why we have times 100. So what we can do is that we can change the formula a bit, so that instead of 16%, we write 0.16 and eliminate the 100. Because essentially we're just dividing both sides, since this equals to 16. So you have output over input equaling to 0.16. In this case, output is 3.5. Okay, 3.5 times 10 to the power of 3, because this is kilowatt. Over, I'll just move this one down. 3.5 over the input, which is what we actually want to calculate, equaling to 0.16. So the input here, the input power, will be 3.5 times 10 to the power of 3 over 0.16. Now you can just plug that into your calculator, and that will equate to 21,875. And since here we are looking into, again, two significant figures, your answer has to be to two significant figures. So 22,000 what? 22,000 watts. That rhymed. So 22,000 watts. Okay. So far so good. We can move on to the next part. The solar panels produce direct current, and household appliances uses alternating current. Okay, now state the difference between alternating current and direct current. Okay, so this is a memory item. You have to make sure that you memorize this one and understand it very well, because you will see this one quite a lot. And if not in the case where they will ask you the question literally, they may just use the idea of alternating current and direct current in calculations. So you have to memorize and understand. And of course, it's easier if you understand first. So, if you want to visualize it, then the direct current here would look something like this. Now, this will be your zero axis. This is DC. This is direct current. However, if you want to look at the alternate current, again, this is your zero axis, it will look sinusoidal, like a sine graph or a cosine graph. Depends. So basically here, that will be AC. You can see this is direct current. It is just basically a constant supply of current or voltage, while AC, aka alternate current, it basically fluctuates. It varies. It goes positive, then negative. And AC is actually better for longer range. But this is a topic for another day. So the difference between them, based on these two graphs, you can already tell what's going on. You can say that DC has a constant voltage, while AC has a fluctuating voltage. You can also say that DC contains either positive or negative values, while AC can have positive or negative values. Up to you. Since this is only a one marker, you can choose either. You can choose both if you want to, but personally, I will choose only one. The point I will go for is the idea that DC has a constant current, while AC has a fluctuating current. So, DC current produces constant voltage or current, up to you, while AC produces fluctuating current. Fluctuating current. Okay. Now on to part D, or off to part D. Suggest one advantage of storing energy in the large rechargeable battery. Okay, so looking back at the diagram here, we can see that there is a large rechargeable battery to the side. Now, why do we need this? Now, for solar panels, from the name, they only work when the sun is up. So, what will happen when the sun sets, like after midnight, let's say? Will the house not have any power and the house owner has to sleep with no AC in the middle of this heat wave? Of course not. The large rechargeable battery will basically act as a reserve in which after the solar power is cut because there's no more solar energy from the sun, then essentially what's going to happen is that this rechargeable battery will supply energy to the whole house. So this will ensure that the house owner will always have electricity 24/7. So to ensure electricity is available at night, or around that context, you can say also for example, when let's say there is dust on the solar panels, you can say that. However, the most reliable point here is talking about the night, because this is what will happen daily. Okay, now calculate the charge that flows into the battery when there is a current of 4 amperes for 2 hours. Okay, now this one here is a formula being Q equals to IT. A way to memorize it is that IT, it's like information technology. This is like a synonym that I used to basically memorize this one. So Q equals to IT, and Q because computers have charge, so we can use this one here. Or more specifically an acronym, yeah. So Q here will equal to 4 amperes times 2. Can we just say 2? No, because that is in hours, and our answer has to be in seconds. So first of all, you have to convert that to minutes, so 2 times 60, and then 2 seconds from minutes, which is 60 again. That will basically be 8 times 3,600. And the answer here will be 28,800 coulomb. That is the unit for charge. Once again, here we are using two significant figures, so we will do the same with the answer. So it will be 29,000 coulomb. Okay, that is perfect. We're done with question number 3. Off to question number 4. Okay. Figure 4.1 shows gas trapped in a cylinder by a piston. Part A states the volume of gas is 240 centimeter cubed. The piston is pushed to the left and is held in its new position. Okay. The pressure of the gas increases from 1 times 10 to the power of 5 Pascal to 1.4 times 10 to the power of 5 Pascal. The temperature of the gas remains constant. Calculate the volume of the gas when the piston is in its new position. Okay. All right. So this one here, it uses the law that we're all familiar with, or at least we have seen it, which is P1 V1 equals to P2 V2. Okay, so we can apply this formula here. We know that the volume of the gas, the initial one is 240, and the initial pressure was 1.0 times 10 to the power of 5. So that will be P1, and that is P1. So 1.0 times 10 to the power of 5 times 240 centimeter cubed. Now, why haven't I converted that to meter cubed, although that is the SI unit? That is because you have to be very careful and look at the question. You see here, volume that's given in centimeter cubed. You should not convert here to meter cubed. So be very careful. And the new pressure here will be 1.4 times 10 to the power of 5 Pascal. Okay, and that's multiplied to V2, because we don't know what V2 is. So just a quick rearrangement of V2 to be the subject. That will be 1.0 times 10 to the power of 5 times 240 divided by 1.4 times 10 to the power of 5. Okay, that is great. So let's use our calculator, and that will be 171.4 centimeter cubed. Okay, let's look at the question. We use two significant figures, so we should apply the same. Our final answer will be 1700, or not actually, that's just 170. It's not 1000 yet. So 170 centimeter cubed. It's already written, so I don't need to write that again. So that will be our final answer. Okay. Part 2. The area of the piston in contact with the gas is 1.9 times 10 to the power of negative 3 meters squared. Calculate the force exerted on the piston by the gas when the piston is held in its new position. Okay. Notice here, when it's held in its new position, the new position is after the volume became 170 centimeter cubed, and after the pressure was 1.4 times 10 to the power of 5. So here we can just apply the formula of pressure equals to force over area. So we rearrange for F to be the subject, being force equals to pressure times area. Okay, F equals to PA. Good. So pressure here, the new pressure will be 1.4 times 10 to the power of 5 times the area. Okay, now the area here is already given, so that's easy. So 1.9 times 10 to the power of negative 3. It is already in meters squared, so we don't need to convert anything. So it's just a simple plug into the calculator equation. And what do we get here? We get 266 newtons. Once again, the question is to two significant figures, so you should put your answer accurate to two significant figures, making our final answer 270 newtons. Okay, on to part 3. The distance moved by the piston is 0.030 or like 36 meter. Okay. The average force exerted by the piston as it moves is 220 Newton. Calculate the mechanical work done by the piston. State the equation you use. Okay. So work done will equals to force times distance. Distance is given. Force is given, so you just plug it in. So 0.036 times 220. Okay, that's a straightforward question. I like that. So that would be 7.92 Newton meter. Since you have newtons of force and meters for distance. And correct to two significant figures, that will be 7.9 Newton meter. Okay. Now part B explains in terms of particles why gases can be compressed but liquids can't. Okay. So if we want to draw the structure or like the estimated shape of a liquid, now first of all, this is a solid, just for reference. We can see it's neat, it's organized, it's in a batter, a solid batter. Meanwhile, liquids, they just glide over each other. There isn't really a pattern, really. One overglides the other, and it's a mess, basically. This is what liquids are. Although, yes, there are like some spaces in between, they are kind of negligible. Like they're just there because these molecules or particles are able to glide over each other. That's really it. We can't really use the space to further compress. Meanwhile, for gases, the spaces are huge in comparison. So these two particles can be put together, so as this one over here. So this is why gases can be compressed, but liquids and solids can't. So gases contain big spaces in between particles, while liquids have negligible separation. Negligible being almost non-existent. Negligible separation. Okay, sounds good. We're done with question number 4. Alright, so here we have question number 5. There is a large bottle of water on a road. The water in the bottle evaporates. Describe how evaporation from the bottle occurs. Use ideas about particles in your answer. Okay, alright. So this is, it's actually good that it's a 2 marker, because usually that is actually a 3 marker. So 2 markers is actually good. So here, what's going on is that let's say that here we have a tub. We have water here. So essentially when evaporation occurs, and this is evaporation, okay, this is evaporation and not boiling. For evaporation, here the water molecules have various levels of energy. Some molecules have a lot of energy, some molecules don't have that much energy. Typically, the molecules, or like there are molecules at the surface that have high energy. Okay, like for example, this molecule here and this molecules here have high energy. Because they have high energy, which is like due to like, let's say high kinetic energy. So if they have high kinetic energy, then they are more likely to break free of the intermolecular forces and evaporate into a gas. So this is essentially what's going on here. What's going on is that the molecules with a high kinetic energy at the surface will overcome the intermolecular forces, causing them to evaporate into a gas form. That's basically what's going on. And make sure that you mention at the surface, because this is evaporation and not boiling. Boiling occurs throughout the medium here. However, here it only occurs at the surface. So molecules of high kinetic energy at the surface overcome the intermolecular forces, causing them to evaporate into a gas. Okay, this is good. Now state and explain one change in the weather that causes a faster rate of evaporation. Okay. Now typically this would be, we have two possible scenarios. Either the wind speed or the temperature. The temperature will cause the kinetic energy itself to increase, so there are more molecules with higher kinetic energy, and more molecules can evaporate. Meanwhile, for wind speed, what's going on is that the molecules, yeah, they have high kinetic energy, and they evaporate initially, and they become a gas, However, what's going on is that instead of actually evaporating and going into like far away as a gas, they would only kind of like bounce over the surface and then return back into the surface of the liquid. So if there is high wind speed, then this initial jump will be backed by wind that can carry it over into a further place that's away from the bottle. So the water can come back. This is basically what's going to happen. And I will use this example here. So wind is able to carry molecules over the surface, preventing them from returning into the liquid or to the liquid. Okay, this is a good answer. So we can move on to part B. A car travels on a dry road. The driver presses the brakes. The car travels a distance before it comes to rest. This distance is called the braking distance. State and explain how the braking distance changes with the road is wet. Okay, so this is kind of similar to this part here, which is also about traction and about like grip. So essentially, when the road is wet, the car won't have grip on the surface of the road, causing it to like skid and also to have a larger braking distance. So when there is water, the friction will decrease, so it will take more effort for the car and of course more distance to stop. So that's basically the idea. Wet surface results in lower friction, resulting in increased braking distance. So this is a state and braking. State and explain question. Okay, so you have to state what's going on, what's going to happen, in which like that the braking distance will increase, and you have to explain why, in which the wet surface will result in lower friction. And that's question 5 done. Let's see what we have here. Question 6. Okay, so figure 6.1 shows successive crests of a water wave approaching a boundary. For part 6a1, the speed of the waves in region B is lower than the speed of the waves in region A. On figure A, or in figure 6.1, draw the crests of the waves in region B. Okay. So, the golden rule is that in a region in which the speed is lower, the refraction will occur towards the direction of the normal. So if we want to extend this line over here, now this is basically the incident, the place in which the line was incident. If we want to draw a line, now typically we should draw it dotted, but here since I'm using software, then I can probably do that here. So this is the normal. So instead of the line going straight on or going towards the boundary, it will instead go towards the normal. So it will look something like this. And you have to make sure that the distance between each crest, between each wavefront here, is the same. So, and you have to make sure that the line is perpendicular. So it should look something like this. Distance should be roughly the same. Now, of course, I don't really have access to a ruler over here. However, in your actual exam, you will have a ruler. So you have to make sure that you utilize it and ensure that the distance is constant between each as well as that of the diagram. So if here, let's say the distance was about 1 centimeter, you have to ensure that the distance here is 1 centimeter throughout, as well as here, of course. So 1 centimeter, you have to make sure that it is constant. Because the wavefronts here, the wavelength will not change. It's only the direction that changes. Okay. Now state the wave effect that occurs as the wave crosses the boundary between region A and region B. That, of course, is refraction. Okay, part DI. Light can be totally internally reflected when striking the boundary between two different regions. State two conditions that are necessary for total internal reflection to occur. Okay, the first condition that we need is that we have to ensure that region A is slower than region B. Why? Because if region A was slower than region B, like of course it means that region B is faster, this will ensure that the light will be reflected more towards the boundary. So if it was slow enough, region A was slow enough, it can cause reflection like that. So that's the idea. So incident medium should be slower than the new medium. Okay, and also the angle of incidence here, the angle of incidence, it has to be greater. Actually, this is the angle of incidence here, because that is the normal. The angle of incidence has to be greater than the critical value, right? Is that right or no? Okay. So you have to make sure that the angle of incidence is greater than the angle or the critical angle. So that's what you have to write. Angle of incidence is greater than critical angle. Is greater than critical angle. Okay. Now for part B2, state two advantages of using optical fibers for transferring high-speed broadband. Now there are a lot, but they only ask for two. One of which is that it's able to hold high data. Okay, so it can transfer high data. So transfers high data, like high amounts of data, and also it's able to transfer them quickly. So quick transfer rate or high transfer rate. Okay, so that is that for part for question 6. Okay, so far so good. We're done this much so far. We have about like half the paper, I think. Okay, yeah, about half the paper. So, or a bit less actually. So question 7. A circuit contains of an AC supply and two lamps. The lamps are connected in parallel. Draw the circuit diagram. Okay, AC supply. So AC supply, first of all, it looks like this. This is the symbol of AC supply, like so. That's AC. So with that out of the way, we can draw the wires. So we have two lamps. They are in parallel. So let's first draw the first lamp in series, like so. So far we only have one lamp. To draw the other lamp that is parallel, it would look something like this. Now here there is no mention of any switches or anything at all. So since there's no switches, there's nothing, so we don't really have to draw them. You shouldn't draw anything like a switch if they didn't ask you for or to. So this is a simple diagram. That's really all what you need. Now for part BI, the electromotive force EMF of the AC supply is 230 volts. When connected to the 230 volt supply, the resistance of one lamp is 1200 ohms. The resistance of the other lamp is 800 ohms. Calculate the current in the 800 lamp ohm. Okay, alright, so the current. So first of all, we know that R equals to V over I. So I equals to V over R. Okay. So we need the voltage and the resistance. We know the resistance, which is 800. The voltage is constant because it is, after all, parallel. So this is 230. This will be 230. This will also be 230. So the current I will be 230 volts over 800 ohms, just like that with the calculator. And that will give you 0.2875 amps. So if you want to get that to two significant figures, not if you want, but you have to actually, then that will be 0.29 amps or amperes to be more formal. Okay. Part 2. Calculate the energy used by the 800 ohm lamp in 5 hours. Give your answer in kilowatt per hour. Okay. First of all, we know that P equals to IT, or IV actually. IV. P equals to IV. That's power. Energy, or like power, equals to energy over time, of course, which is like the same as work. So if you substitute that, then that will be energy over time equals to IV. So energy equals to IVT. So what do we have here? Energy will equal to the current that we calculated. It's better that you use the original current being 0.2875 times the voltage being 230 times the time being 5 hours. So 5 times 60 times 60. Okay, so that will be times 130 times 5 times 60 times 60. That should be about 1,109,250 watt per hour. Watt per hour. But we have to convert that into what? Into kilowatt per hour. So we divide by 1,000. So that will essentially be 1,190.25 watt per hour. Kilowatt per hour, actually. To do significant figures, that will be 1,100 kilowatt per hour. And that is our final answer. Okay, part 3. Calculate the combined resistance of the two lamps in this circuit. The combined resistance. Okay, so essentially 1 over RT equals to 1 over R1 plus 1 over R2. So if you want to find RT, that will be 1, the reciprocal of course, 1 over 4, 1, or R1 I mean, R1 plus 1 over R2. Of course, you can also calculate the value of 1 over RT in your calculator, and then you flip the fraction if you want to. But personally, I use this method here. So what do we have here? RT equals to 1 over, I think, 800, isn't it? Okay. So one lamp is 1,200. The other is 800. So it is 1 over 1,200 plus 1 over 800. Okay, so if you want to put that, that will be about like 1 over 480, which means that the final answer will be 480 ohms. That will be the combined resistance. And you have to make sure that you use and put the unit. Do not forget. Okay, so that is question 7, is it? Yeah, question 7 done. Then move on to question number 8. Okay, so 8a, state what is meant by a magnetic field. Okay, so this is also a memory item. You have to memorize this one. It is a region in which a magnetic pole experiences a force. A magnetic pole experiences a force. Okay, so for part B, figure 8.1 shows an ammeter connected to a coil wound on a thin plastic cylinder. A small trolley is placed on a curved track which passes through the cylinder here, okay? So the trolley goes like so, and then back, and so on, like a pendulum basically, or a pendulum. So the trolley is released from the position shown in figure 8.1. It travels through the coil from right to left. The trolley travels back from left to right, like a pendulum, as I said. It has a lower maximum speed when it travels from left to right. Yeah, so basically it regressively slows down. So this is the highest speed, then the next time it becomes slower, and then slower, and so on. So, state why there is a lower maximum speed when the trolley travels back from left to right. There are two reasons. The first reason is something that we've mentioned a lot this paper, which is friction. So, friction results in decreased speed. Because after all, friction is an opposing force. This is one way of putting it. The second way of putting it also is that you can talk about the actual mechanism here. So this trolley here has a magnet. Here, this is a coil, and here Lenz's law will apply. So when the trolley enters here, Lenz's law will apply. So there is an induced current, an induced EMF also, and this will result in a magnetic force. This magnetic force coming from the coil, the induced magnetic force, will oppose the magnetic force caused by the trolley. So it's kind of like someone is pushing the trolley backwards. So this will cause the trolley to have a decreased speed. Okay? This is the idea. But personally, I will just write the shorter version, which is just friction. That's it. But if you want a more answer or like an answer that's more related to the question over here, then you can just say what I just said, which is basically linking Lenz's law to this idea. Okay, part 2. It's also about Lenz's law. Figure 8.2 shows a close-up view of the ammeter. As the trolley enters the coil moving from right to left, the ammeter needle deflects to the left and then returns to zero. State and explain any changes to the deflection of the ammeter as the trolley enters the coil when moving back from left to right. Okay, alright, so essentially here, what's going on is that when this trolley enters the field, or like enters the coil and then generates a field, as we said, then the ammeter will show the reading that will deflect to the left. This is as what? As the trolley is approaching. Now they're asking that if the trolley was here on its way back, what will happen to the reading? Now, after all, it will also face the direction of the coil, which means that the needle will also deflect to the left. It will not go to the right. It will only go to the right as the trolley was leaving the coil. Be very careful. Other students would fall in this trap. So, essentially what's going on, or like what we should write here, is that the needle will deflect to the left. Now this is because there isn't any change to the magnetic field direction. You can say that actually. I think I should write that. So due to no change in magnetic field direction. However, it won't be the same value. So it will deflect less. So deflection will be less. Why? Because we said that initially, or here, in part I, that the trolley will have a lower speed here. So because of the lower speed, it will of course go back to the coil with a lower speed as well. And due to Lenz's law, because here we have a lower speed, then the value of deflection, or like the value of the EMF, induced EMF, for the current also will be lower. So the deflection will of course also be subsequently lower. So this is basically what we are going to say here, what we're going to write. Deflection will be less. Deflection will be less. Resulting, or like not resulting, but due actually. We have to mention due first. Due to lower or lower, I'd say. Lower or smaller approach speed. Now we say resulting. Resulting in what? In decreased induced EMF and current. Decreased induced EMF and current. And that's that. We are done with question number 8. Okay. Okay, so figure 9.1 here for question number 9 shows a beam of radiation in a vacuum. The beam contains alpha particles, beta particles, and gamma radiation. Okay. The beam enters a region where there is a strong uniform magnetic field. The direction of the magnetic field is into the page. On figure 9.1, draw and label the paths within the magnetic field of, first, alpha particles, second, beta particles, and third, gamma radiation. Okay. Okay, this is into the page. So here you have to use Fleming's left hand rule, okay? Left hand. So if we do a small Google search to show you like what the Fleming's left hand rule would look like, then it would look something like this. So this is what Fleming's left hand rule would look like, in which your index finger will be the magnetic field, your middle finger will be the current, and our main focus here will be the thumb, which will act as, of course, the force. So if we actually apply it here, then it would be something like this, okay? Okay, so essentially it would look something like this for the alpha. It will go upwards, because if you use your Fleming's left hand rule, then your index should point towards the screen, your middle will point towards this direction here, and because of this, of course, your thumb should point upwards, which is the direction for the alpha. It would look something like that. So this here will be what? This will be alpha. You have to label it alpha. Now, on the other hand, for beta, which is Q, the beta particle, it would be like so, straight down. Now, why is that? It's actually like this more so. Essentially because beta particles is smaller. It is lighter. So essentially, it won't take that much force to deflect it by as much as the alpha particles. So that'll be part 2, and that's why you have 2 marks here. The other mark is for showing that the radius here is smaller. And last but not least is the alpha radiation, in which it's not affected, and so it will just go straight through. That will be the gamma, while this one here will be beta. Okay. Next part here. Table 9.1 shows 5 radioactive sources, the mean type of radiation emitted by each source, and the half-life of each source. Define half-life of a radioactive source or isotope. Basically, the definition of half-life is the time taken for the number of nuclei to have. And that's the definition. A1 marker. Okay. Now for part 2, figure 9.2 shows a simplified diagram of a machine that produces thin sheets of aluminum of constant thickness. Okay. The radiation detector is used to measure the thickness of the aluminum sheets and control the gap between the rollers. State the most suitable radioactive source in table 9.1, being this, for the machine in figure 9.2, which is this one here. Explain why this radioactive source is the most suitable and why the other sources are unsuitable. A 4 marker, okay. So this is like about like half of your marks already, for this question at least. So, first of all, we care about two things. We care about penetration and we care about the longevity. So, regarding the longevity, we want a source that has, let's say, a okay-ish half-life. We don't want it to be too short because we don't want to keep refilling the source. So we don't want Q or S. It's either P, R, or T. And well, you can see that each are either alpha, beta, or gamma. So this is our second choice. Our second choice is to choose between alpha, beta, or gamma. Now here, beta will be the best choice. Why? Because gamma, although it has the best half-life, alpha by itself would immediately be stopped by the aluminum. So it won't even have a chance to reach to the detector, which won't be practical, of course. When it comes to gamma, it's the exact opposite. All of the gamma will pass through. So really, like a reading for both for gamma and for like the alpha, both of them are useless because it's either nothing or everything. We don't want that. We actually want to have a variation in the value that we're able to actually judge the thickness. And this would only be possible with beta. So it will be R. This is our answer, R. And explanation is that R contains good half-life or long enough half-life that doesn't require to be refilled frequently. Okay, that's for one. Alright, now our second point here will be about the alpha. So alpha will immediately be stored by the aluminum sheet. So of course it won't reach the detector. While gamma will completely pass through the sheet, resulting no change in the reading. No change of the reading. No change of the reading. Of the reading. Okay, so far so good. And then here we talk about the beta and like basically what advantage it gives us. So for beta, so beta will provide moderate penetration, let's say. Just maybe to moderate penetration. Resulting in a change of the value of like the detected value, depending on, of course, the thickness. In a change of the detected value, depending on the thickness. And that will be our answer. So we need to assess all of these in order for us to get the full credits. This is probably the lengthiest question here. Okay, now last question here. which is question number 10. Fill in the gaps in a description of how an accretion model explains the formation of the solar system. So the planets nearest to the sun are small and they are small and rocky. So for example, us, Earth, or like Mercury, the ones that are closest to the sun, even Mars, are rocky. Meanwhile, the ones that are later on, or like further, such as like let's say Neptune, for example, Jupiter, these are gaseous. Okay, so are large and gaseous. All the planets were formed when a cloud of gas and dust collapsed due to, I think that you already know, due to gravity or gravitational strength, or gravitational force, actually. That's a bit better. And the rotation of material in the cloud forms an accretion disk. You have to know this. An accretion disk. I'll actually just show you what an accretion disk would look like to visualize it. So for example, as you can see, like to a young star, there is a disk of gaseous materials and whatever that is surrounding the young star. That is the accretion disk that we're talking about here. So this is something that you have to make sure that you nail, as it's quite common to be asked for, especially like in, let's say, fill in the blanks type of questions. Okay, the time taken for light to travel from the moon to the earth is 1.3. Calculate the distance of the moon from the earth. Give your answer in meters. Okay, first of all, that's interesting. First of all, we need to understand that the speed of light, c, is 3.0 times 10 to the power of 8. And also, we know that speed equals to distance over time, which means that distance equals to, this should be velocity, by the way, velocity times time. Now, you don't say s here. It is still speed, by the way. But why I put v is because s means displacement. So you have to be careful. So that would mean that the velocity being 3.0 times 10 to the power of 8 multiplied by 1.3. That will be the distance. So if we want to actually calculate that, then that would result in 3.9 times 10 to the power of 8 meters. And that will be our answer. Alright, the final question. The last one. The Whirlpool galaxy is 2.3 times 10 to the power of 7 light years from the Earth. The current value of the Hubble constant is 2.2 times 10 to the power of negative 18 per second. Calculate the speed at which the Whirlpool galaxy is moving away from the Earth. Okay. First of all, 1 light year is equal to what? That's the question. It's equal to 4.5 times 10 to the power of 5. That is what? That is 1 light year. Okay? So, moving on, and it's actually 4.8, yeah? So 4.8 and 4.5. The 5 is here. So 4.8 times 10 to the power of 5, that's 1 light year. So, we have 2.3 times 10 to the power of 7 light years. And we know that Hubble constant equals to what? It equals to velocity over distance. So if we want to get the velocity or the speed, that will be Hubble constant times the displacement or the distance. Which means that our answer will be Hubble constant being 2.3 times 10 to the power of 7 and 1 light year, which is essentially distance. It is the distance traveled by light in 1 year. So that is 4.8 times 10 to the power of 5. But we don't leave the answer like this because this is only for 1 year. But we have 2.3 times 10 to the power of 7 light years. So that's of course in meters. So we want to convert light years to meters in order for us to actually get the answer. So if we plug that into our calculator, then this will be our answer. Our answer should be, if we didn't do anything wrong, 2.5 times 10 to the power of 20 meter per second. That is, of course, rounded to what? To two significant figures. And voila, we are done with this paper. So that's that regarding this paper. We can do paper 5 for paper 2 next. So please make sure that you subscribe to Manarat Academy and see you all in the next one. Goodbye.